Hello! Today we will present our second course project, entitled An IoT-powered noise monitoring system. The challenge that we decided to tackle consisted on designing and implementing an IoT application. In order to respond to this challenge, we had to select a use case, and after some brainstorming, we ended up with the question, how can we monitor the indoors or outdoors noise level? This is useful for various reasons, but namely because we can only sustain a limited noise level if we want to safely and productively carry out our daily activities. Ultimately, this idea led to the two main goals of the project. The first goal was to develop an IoT application to support the monitoring of noise level in a given location. And to do so, we selected two different middlewares, the FireWare and MQTT ones, and secondly, we wanted to compare the two middlewares in terms of usability, latency, and overhead. The FireWare architecture comprises three nodes, each of which has specifications that you will see in the slides. Our first node is an Azure virtual machine, hosted in a server that's located in the Netherlands. It serves as both a broker, since we are dealing with a middleware of type publish-subscribe, and a web server that is used to access the application's dashboard to monitor the noise level. The Android phone, which acts as our second node, is responsible for collecting the noise level values through its microphone and to publish those values to the broker. Finally, a laptop is used as an access point to the dashboard, to which we can connect via a browser. Moving on to the design of the system, we'll now try to explain the life cycle of context information. First of all, we define context information as the data that can be generated by multiple sources, either IoT devices or not. In our architecture, the context information is the noise level, which is captured by the Android mobile device. Once a noise entry is generated, the phone simply makes a put request to the Orion context broker. This action requires a prior registration of an entity in the broker, as we need to inform it that an entity of type room exists and has an attribute called noise level. This interaction, essentially a post request, is only performed once so that, in the next interactions, we may inform the broker about which entity's state we want to update. The context broker, on the other hand, is a central piece here. It is a component that maintains a representation of the state of the entities in a MongoDB database. But the context broker alone is not sufficient as an intermediary for the exchange of context information, as it holds only the current state of the entities. Given that the broker has no memory, we need to employ yet another component, called sth-comment. It is responsible for managing the evolution in time of context data that is registered in the broker instance. For that purpose, we issue a single post request to enable sth-comment to subscribe to changes in the context state of the room entity. That means that every time the noise level is updated in the broker notifies this component, which in turn updates historical context information. Finally, our web server, also running on the virtual machine, collects historical context information through sth-comment's API and generates a user-friendly dashboard that can be accessed over a web browser.
MQTT architecture has three nodes to set it up in this experiment. First one is MQTT Docker Windows that I use it for the broker and a web server. Second one is the mobile phone that I use it to measure the noise level sensor and make it about the MQTT client publisher. And finally, a laptop that makes the access point for the client subscriber. So MQTT is a protocol that defines the types of entities in the network, a message intermediary, and a number of clients. The intermediary is a server that receives all the messages from the clients and then redirects them to the clients in relevant destinations. Starting for the mobile phone that publishes the sound level, it makes the MQTT client that publishes the message on a subject by sending the message and the subject to the intermediary. Meanwhile, a TCP connection, or it could be also an encrypted TLS connection for confidential messages. So then the MQTT broker makes about an intermediary, where a client is anything that can be interact with intermediary to send any received message. A client can either be an IoT sensor in the file or a data central application that process IoT data. Then, by a web server, it sends.
We found many challenges along the way, but with those challenges came also some benefits. We first discovered that the microphone that we intended to connect to Raspberry Pi was not available after all, so we had to opt instead for a solution that was promptly available, that is to say, to use our mobile phones instead. The benefit of this solution is that we can move our phone to different places and continue to collect noise values, which would have been much more difficult to accomplish if we had stuck to our original plan. On the other hand, we found that the two next challenges were common to both middlewares. First, the packages of the two brokers were linked to the documentation, but unfortunately the links were broken, and we couldn't find elsewhere the software that we needed. That is why we had to opt for the corresponding Docker images, which proved to be much easier and faster to set up. And finally, our experience with this project showed us that the middleware's documentation was spread across multiple sources and not all of them were up to date. And this fact hindered our progress, so we had to resort to community forums and the GitHub issues for help. You can now take a look at the visual portion of our architecture. Please note that the Android API, which acts as an interface to the microphone, gives us a value of the sound wave amplitude A, but in order to obtain the intensity of the sound, measured in decibels, we use the following formula and provide the amplitude value as an input.
As we can see in the video, a decibel measure app has been used to measure the sound level that is recorded by a mobile phone and sent to the MQTT broker, that meanwhile a script is sent to the MQTT client, and this shows the different values of the dBs that was sent meanwhile the MQTT broker to this program client to subscribe it.
Now, over to the experiment, we measure the performance of our architecture in terms of latency and overhead, and between the network and
Talking about the experiment do it with MQTT, I measured the latency of the different levels of security that MQTT has. So, in these graphs, we can see the average latency tends to decrease slowly as the test progresses. The values are significantly higher in the start of the test rather than the end. This is expected because of caching and reducing overhead is an already established connection. So, looking for the usability of MQTT, this protocol is oriented to sensor communication. That's why it consumes very little bandwidth, minimum overload, and can be used in most embedded devices with few resources. It is focused on sending data in applications with low bandwidth is required, so it characterizes a load it to avoid a really low consumption as well as requiring very few resources for this operation. Finally, talking about lesson learned, the most thing important is about what we learn about communication of the Internet of Things. This one is a dynamic global network infrastructure with self-configuration capabilities based on standard communication and that they operate between each other where physical and virtual things have identity, attributes physical and virtual personalities using intelligence interfaces being seamlessly integrated into the network of information. So, as we can see in these three basic pillars of knowledge, the design of things that makes the hardware part, the communication infrastructure design that is more the telematic part, and the decisions making that is more the semantic and the rational things, make the IoT phenomenon will be in the found intersection zones of these three areas. The third definition comes from a computer graphic, which quickly and effectively summarizes the basic concept of this technology. A smart system and IoT are driven by a communication of sensors and actors, connectivity, and people and process. So according to this vision, sensors And actors create a digital nervous system, and thanks to the connection, the availability of data is enabled with transmitted, stored, combined, and analyzed between systems that integrate data, people, processes, and other systems. Furthermore, this makes the three fundamental principles of IoT: things, connection, and process. Thanks for your time.